Okay, so these are what I refer to as focus activities. Those folks who I've had before are already familiar with these, but this is another way for me to go ahead and help you with your average, basically almost just handing you a grade. These are going to show up maybe once or twice a week, and we do sets. You'll notice this one, it's number 1. It tells you the 6 weeks, so it's going to be real easy to keep track of them. I'm thinking in this first set, we're only going to have probably 3. I'll give you, well, you got the second one. We won't cover it until Friday. You'll get your third one next week. And however many we have in a set, at some point, I'm going to say, okay, I need you guys to go ahead and turn those in for me. So really, it's problems that we look at together at the beginning of class. Could be something that goes along with the current material. Maybe it's something I want to remind you about that you haven't seen in a good while. Or maybe it's just something brand new that I don't want to spend an entire class on. At least I can introduce the idea. Okay, so it's going to cover, things like that. And we're currently talking about intersection and union. So I thought this is a perfect opportunity to solve what's called a compound inequality. All right, so we know inequality statements. These guys right here, like 5x minus 3 greater than 2, 5x minus 3 less than or equal to 8, but I want to take the intersection and the union of those sets, the answers that I get. Okay, and you remember yesterday when we were talking about the notes, conjunction was an intersection, disjunction was a union. Okay, so let's go ahead and walk through these and I'll show you what we're going to do. So we know how to solve an inequality. If you don't, all I want to do is isolate that x, right? So first off, how do I get 5x by itself? Okay, so I'm going to add the 3. So the first one, I'll go ahead and show the steps. So I'm going to add the 3. Okay, those are going to cancel. So 5x is greater than 5. There you go, because the last step is going to be division. I mean, that's even why I wear glasses, because it helps me with division. It helps me with division. Okay. I get it. You don't want it, but you get it. Okay. Anyway, yes. Oh, because what's the opposite of multiplication? Division. So if I want to get rid of multiplying by 5, then I have to divide by 5. So see, now these guys are going to cancel, and I've got x is greater than 1. So that is the solution for this. Any value larger than 1, but not 1 itself, is going to make that a true statement. Okay? Now I would encourage you, look at this other one right here, 5x minus 3 is less than or equal to 8. You would do the same thing. Go ahead and add the 3 over, divide by 5, but see if you can do it mentally. If you have to write out the steps, there's nothing wrong with that, okay? Everybody has to do that from time to time. But the more you're able to do in your head, the stronger you're going to become. So let's just think through it. If I added the 3 over, 5x would be less than or equal to 11. So then I divide by 5, x would be less than or equal to 11/5. Very good. So x would be less than or equal to 11/5. So this is the answer for the other inequality. Is everybody with me so far? Now, this is what makes it a compound inequality. I want to find the intersection of these two answers that I got. And I want to go ahead and show it in the different ways that we've been looking at in class. So I'm going to start graphically. Okay, so we're taking the intersection. I'm going to go ahead and draw the graph here. Now, the two values in question, I'm going to go ahead and put them on my line graph. All right. Now, I'm not going to draw on the line itself. I'm going to go ahead and do it above. This is how I got accustomed to doing it. If you like it, great. If you don't feel you need to do it, don't worry. You can go straight to the answer. So I want everything larger than 1, right? Okay. So I'm going to start here, and I'm going to graph greater than 1. But how do I show it's not included? An open circle. Okay, just like that. So there's the graph solution for x is greater than 1. Well, now I'm going to do the same thing for the other one. I want everything less than 11/5. So I'm going to shade it to the left. But how do I show equality? Closed circle. There we go. Now, I want to use this to help me write my answer in different ways. Okay, so I'm going to go ahead and draw the actual line graph answer now. So I'm going to put 1. I'm going to put 11/5. What is the intersection looking for? Was it the combination, or was it everything they shared? everything they shared. And that's why I like to do it this way. Because if you go ahead and graph it, where they overlap, that's what they share. So I can tell that I should only be shading between 1 and 11/5. Now the only thing I have to figure out, do I put open circles? Do I put closed circles? What do you guys think? Open and closed. This one right here, he's not included, so I'm going to follow suit. This 11/5 was included, so I'm going to close him up. Okay. And like I said, for me, it makes it really easy to see how I can get my answer if I graph above a line. But like I said, if you don't feel you need to do that, don't worry about it. Okay. Now, I also want to go ahead and show this answer in interval notation. So this has specific places where I'm going to start and stop. Okay. So we start at 1, comma, we end at 11/5, right? How will I close this up? Okay, so parentheses tell me it's not included, and then the bracket because the 11/5 is. And your answers, you're going to notice they should be mimicking each other. See, the graph is telling me I want everything between 1 and 11/5, and that's exactly what the interval notation is telling me as well. Okay. Now, there's one other way I want you to go ahead and show this to me, if I were to ask. I want you to write it as a solution set. So this would be all x, what's that? Such that, and then here's my restriction. This is where typically you're going to go ahead and write your answer using the inequalities, the less than and the greater than. Now, because of this graph right here, because I have one that's less than and one that's greater than, we can write this as what's called a compound inequality. I could say 1 is less than x, which is equal to less than or equal to 11/5. Okay. And now you'll notice it's the first part that might kind of throw some people off right here. Is x greater than 1 the same as 1 less than x? Yeah, it looks like the symbol has reversed itself, right? But you want to be careful, it's actually saying the exact same thing. Like if I were to say 8 is greater than 7, is it true to say 7 is less than 8? That's what's happening here. Okay. Just think of that inequality as an arrow. It's always going to point towards the smallest value. Okay. All right. So that's why I'm able to pull these together. And that's it. That's number 1. Okay. What do you guys think? Questions? Is anybody not sure about what I did? Okay. Now there is one typo on number 2, and I do apologize again. That should be 5x, because if they're different variables, we can't do anything with them. Okay. Now, do you notice anything between number 1 and number 2? Yeah, they're the exact same inequalities. So see, I'm going to end up with the same 2 sets, the same 2 answers, but now we want the union of the 2. Okay. So this is going to give me different answers because we're now not taking the intersection, we're taking the union. So if the intersection was everything that they have in common, then what was the union again? Everything. Okay, so let's start with a graph. So I'm going to draw my answer as a line graph. Well, I want everything greater than 1 or everything less than 11/5. So if I were to take both of those and just combine them, how would that look on my line graph? Where am I going to shade? Everywhere. Okay, they're both going in opposite directions and they overlap. So any value, as long as it makes one of them true, it's good to go. Now, I do have a quick question for you. You notice on number 1, this guy right here, we didn't include him because of that open circle. But why is 1 included in the graph? Why is that okay? That's exactly right. He says it's a less than 11/5. This other answer does include 1. That's why I can just shade the entire thing. Okay. All right. So how would I write this in interval notation? Parentheses, negative infinity to infinity. Now, this is the one exception. If I ask you for interval notation, that's the form that I'm asking for. But if it is negative to positive infinity, if you want to go ahead and put all reals, that is equivalent. I am perfectly fine with that. Okay, either or. Okay. And then for our last one here, I'm going to write it as a solution set. So all x, and was there something we could use instead of a colon? Yeah, that little line, right? So any value of x such that, well, let's go ahead and do this. Let's use our symbols that we were talking about the other day. So I'm going to go ahead and put x. We said that any value of x, any number you can think of is going to make this true. So I'm going to go ahead and use that r. What's that stand for? Okay, all real numbers. But did we have a little symbol that meant is a member of or belongs to? That curvy E. That's exactly right. There you go. That is perfect. What do we think? Okay, and we'll practice this again. In fact, you accidentally got the second focus activity, and you'll notice it's going to be a few more compound inequalities. But here's the important thing about these. Okay, make sure that you put them somewhere safe. We work these together. All you got to do is what? Yeah, just work it with me. Keep up with them. When I call for them, that is another 100 as a quiz grade. Okay. Now, I don't know that I have enough for everybody, but if you're interested, I've got a whole bag of folders over here, and I know it's really easy, well, one, to drop them like I just did, but it's also really easy to lose these slips of paper. Any extras that I have, I'm going to put over here, but sometimes they run out. If you want a folder to keep in this room, say specifically just for your focus activities, you're more than welcome at any time to go ahead and pick one of these up. Okay, at any time. I'll just go ahead and put it right over here in the middle. Completely up to you if you want one. If you feel you can keep it in your binder or someplace safe, perfectly fine. It's your choice. Okay. All right. Good. Well, I think we are ready to go. So we're probably not going to get as very far with the lesson today, and that's all right. One of the main differences that I think we're going to have between our academic level and the IS pre-cal level is I'm going to be much more willing in here to spend time on a topic if we need to. Like if I'm seeing that a lot of people are struggling with a concept, we're going to continue to work with it until you guys feel comfortable. I don't want to just run through just to say, okay, we got everything we were supposed to. I would rather at the very end of the year be able to say, the stuff that we did cover, you guys are good on. Okay? So please ask me questions. All right. Well, let's go ahead and get started. Oh, sorry. My mind's kind of all over the place today. I forgot. What's happening tomorrow again? Don't forget about your quiz. I'll be sending out a remind text tonight just to kind of remind you, probably right after school. Okay? So I know that ends your day perfect, getting a text from your math teacher. Like, super cool. But anyways, the big one, of course, what's next week? The test. We have our test coming up on Thursday. So it's definitely going to cover, intersection, union, the stuff we covered today. My goal is to try and get to piecewise functions by the end of the week, but we'll kind of see how it plays out. Okay? So let's get to some vocabulary. So this, again, is just going to be a review of Algebra 2. So if you already know this, great. If not, perfect opportunity to kind of see where we might have not gotten the material from Algebra 2. So let's fill in these blanks here. X equals the directed distance from the blank, while f of x equals the directed distance from the blank. Anybody think they know? So what was that? What was that? Oh, it didn't say anything? Yes, sir. There you go. Now which is which? The first blank is y-axis. There we go. Okay, so x equals the directed distance from the y-axis, while f of x is the directed distance from the x-axis. Okay, and that makes sense because you think about it. What does f of x really mean? It's just your y variable. It's the notation we use in place of y, because y is what we call the dependent variable. Y depends on x. So if I were to take a look at a coordinate grid, here's the origin. Okay. Well, your coordinates are always in the form x comma y, and x always has you moving what? Yeah, left and right. So either way you go, you are moving away from the y-axis. And then for the y, you're moving away from the x. Okay. Well, good. This one we actually did bring up the other day. The blank is a visual way to determine if a curve is a graph of a function or not. Called it the pencil test or the vertical line test. There we go. The vertical line test. Okay. And then it goes on to say a set of points in a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph at more than how many points? 1 point. Now this one is saying it is a function, so if the sentence was saying it's not a function, then it would be 2 or more points. So this is 1 point. Perfect. Now these three are going to be related to each other, definitely the same concept. The first one says a function f is blank on an interval if for any two x values in the interval, x sub 1 is less than x sub 2, we have f of x sub 1 less than f of x sub 2. This one starts with an I. Does anybody think they might know it? I'm sorry? Oh, not an intersection. It's a good word, though. Okay. Enrique? That's right. Oh, not integer. Another good word. Sorry? Interval? No. Another great I word. What's that? Increase. It is increasing. Did you say that? All right. Okay, I'm old. You know, you got to just speak up a little bit. So I probably can't hear it. So increasing. Yes. Okay, perfect. So again, let's think about an XY system. So we have two X's, and it says that the first X is smaller than the second, right? So I mean, the axes are just number lines. So if I say X1 is right here, you know, then X2 would just be further along because X sub 1 is smaller than X sub 2. Well, remember, you just told me a second ago, f of x, that's what? It's just the y value. So this y value at x sub 1 has to be less than the y value at x sub 2. So let's say I have this y value here that corresponds to x sub 1. Well, I know that the y value for x sub 2 has to be larger. So we just go ahead and draw it higher. So you'll notice, what is it doing? It is increasing. Okay, very good. And now that we know the first one, we're probably going to be able to get the second one pretty easy. A function f is decreasing on an interval if decreasing for any two x values in the interval where again x1 is less than x2. This time we have f of x1 greater than f of x2. So you'd see, you know, something like that. Okay. Now the thing about increasing and decreasing, you always look to see where the y values are doing this, where the y values are getting larger or where they're getting smaller, but you use the x-axis to describe where that happens. Okay, and then we have this last one here. A function f is blank on any interval if, for any two x values, we have f of x1 equals f of x2. Not equal, I mean, it's a synonym to it. It starts with a C. Constant, there we go. Constant. Okay, so yeah, it will just be constant. The y values remain unchanged as x gets larger. Okay, very, very good. Now, depending on your function, maybe your graph will only increase. Maybe the graph only decreases. Maybe a graph will do both. It's very possible because we have a lot of different graphs out there that we're going to look at. So we're going to focus on that more probably tomorrow, maybe Friday, again, depending how far we get. So let's see this one. A function f is blank if for each x in the domain of f of negative x equals f of x. This one starts with an E. Equivalent, again, great word, not the one I'm fishing for. And see, this depends on the teacher. Maybe you talked about it in Algebra 2, maybe you didn't. The word is, and hopefully someone didn't say it and I didn't hear it, even. Did you say it? Oh, okay. Function is even. So what this means is if you have an equation, if I can replace every x with its opposite, simplify and get the original equation, that's what we call an even function. So let me demonstrate. Let's say f of x equals x squared, your quadratic parent. Very simple equation to work with, right? So let's say I'm going to replace x with negative x. Okay, you're always going to replace it with its opposite. Well, what happens when you square a negative? It's always positive, right? So negative x squared would be x squared. So if you're able to plug in negative x and you get the exact same equation, that's what we call even. Okay. In fact, think about the graph of x squared. It's going to look like this. The graph of the function will display symmetry about, so where could I fold in that plane and have the two parts come together perfectly? The y-axis. If I fold on the y-axis. So if you see a graph that has symmetry about the y-axis, more than likely it's going to be even. Okay? All right, we say the two parts coincide because they're like mirror images of each other. You know, it's also what you should do when it rains. Coincide. Okay, let's get. Yeah. I'm very punny. Yeah. It's going to be a long year. Okay. So what do you think about this other one here? A function f is blank if f of negative x equals negative f of x. Odd. Very good. So we also have what we call odd functions. Okay, well, let me go ahead and give you an example. Perfect one, f of x equals the cubic parent, x cubed. Okay, so I'm going to go ahead and replace every x with negative x. So f of negative x equals negative x cubed. Okay. Now, negative x cubed means I want to multiply negative x times negative x times negative x, right? Well, think about it. What's a negative times a negative times a negative? That's still negative. So I'm going to end up with negative x cubed. So see, I know this isn't even because I didn't end up with the exact equation I started with. But if it's the opposite, if every term, oh, we got 6 minutes. If every term has changed sign, then it's going to be odd. Okay. So that's what we call odd. Does that make sense? Okay. So, does anybody remember what x cubed looks like? Say again, me? In a manner of speaking, it does shoot up very quickly. Okay. So a lot of people are showing me in the air x cubed. It shoots up through the origin just like that. Okay. That's x cubed. So now, what kind of symmetry does it have? It's symmetric about something, but it's not an axis. Not a diagonal. The origin. There we go. If something has symmetry with respect to the origin, imagine that the origin is a fixed point, like you're looking at a fan blade, right? Okay, and you got the very center of the blade. If I were to take this graph, if I could spin him just 180 degrees, what is that? Okay, how far of a rotation is that? It's only half, right? Because what's one full rotation? 360. So if I can just go ahead and rotate this halfway, if I end up with the exact same graph, it has symmetry about the origin. Okay. See, this doesn't have symmetry with the y-axis, because if I fold it here, this guy reflects over there, this guy reflects over there. So I don't have the exact same graph. Okay. How much of this is kind of coming back to you from Algebra 2? Kind of, sort of? Okay. Well, let's go ahead and take a look at this one. This will definitely be our last example for today. That's okay. So we're talking about domain and range. So I've got my function here. Okay, just a parabola that's been stopped. So this guy doesn't go forever. Now, when you're asked about domain and range, it's simply how much space does the graph occupy in your plane? I always think of these two questions: how wide and how tall. Okay, so either it's going to go on forever, or it's got places where it begins and ends. So help me out here. How wide is this graph? Where does he start? Yeah, see right here, that's where the graph ends. We're looking horizontally. So he begins at -2. Now, how far does he go? Does he go to infinity? No. Now, we know it's going to go to infinity because there'll be what on the graph? There'll be an arrow indicating that it's going to continue. But this guy just stops. And he stops where? He stops at 4. Very good. So he only exists horizontally between -2 and 4. How am I going to close that up? Parentheses and a bracket. How do I know that? There you go. This end right here has an open circle. This one has a closed circle. Very good. Now, if the domain is how wide, the range was how tall. So we're doing the same thing. You just go from bottom to the top. So how low does he go? The lowest he goes is -5. So I'm going to go -5. How high? Okay. The highest he goes is going to be 3. How will I close it up? Okay, bracket, because that -5 is included. We have nothing telling me that it wouldn't be, but we can't include the 3, same reason we couldn't include the -2. This is another idea that we'll go ahead and practice. Okay, what do you guys think so far? Okay, perfect. We'll go ahead and stop there. Tomorrow we'll go ahead and finish this up, and we'll keep going. Okay, you guys did another great job today. I appreciate it.